Hi, I'm Nick Hale, Senior Researcher at Trillion Technology Solutions out of the Washington, D.C. area. And today I'm going to go over a collaborative and scalable machine learning workflow that we've developed here at Trillion to allow individual developers on our teams to contribute to a given machine learning project, compare their methods and models with one another, and prototype models and train them on the cloud and deploy those models in a production setting with really sort of a seamless integration of parts. And we want this capability to be able to continuously train models and deploy them whenever new data is received as well. So a brief overview of what I'll just talk about today. We'll talk about an overview of the workflow and the components involved in the workflow. And we'll discuss the architecture of how all the components connect to one another to achieve this end of collaborative machine learning. And then I'll go through sort of a sample project as if we were starting a machine learning project from scratch and show exactly how to use the workflow. So some of the objectives that we were looking to get out of this workflow is allowing a team of machine learning researchers to develop on a new machine learning project and collaborate independently of one another, whether they be on an individual developer cloud instance or a local laptop, and allow them to prototype new models without using lots of resources, working on a small set of data, and save costs on that end, and then be able to scale that up to large data set training and ultimately production, model production. And we also wanted easy and experiment tracking and model deployment through this workflow, and a flexible framework that can be used with any cloud platform. So some of the contributions we'll talk about today, the workflow, we'll talk about how to use Git version control with multiple data scientists working together, how to do those branches, those feature branches, and how to scale data science pipelines collaboratively, and also showing how the method is tightly integrated for each step, from developing data science code to experiment tracking to model deployment as well. So here are some of the core components that we are using in the workflow. We have Docker, which is a containerization framework. Kedro, which is we use to create our data science pipelines. MLflow, which is used for machine learning project management, model tracking, experiment tracking, parameter logging, etc. And Databricks is used to integrate our compute with our data stores and allow us to process large data jobs in a very easy sort of integrated way. And we have PySpark as well, which allows us to send jobs in Python to Spark clusters and create those jobs for easy big data processing. And we have a cloud service. It could be this pipeline and this workflow will work with AWS, Google Cloud, or Azure, all the same. So let's get into the components a bit. Some of you may have heard of Docker or have used Docker quite a bit. It's sort of the standard for containerization. So really what we're using it here for is allowing for environment consistency between developers and between training, jobs, execution environments. And Docker is an open platform for developing and running applications. And it provides really a lightweight virtual environment called containers that are sort of loosely isolated from the host machine's operating system. And so our workflow uses standardized container development and deployment, allowing for consistency across machine learning libraries and other software dependencies. So all these libraries and dependencies are ubiquitous for each developer and each machine, each environment we're running on. So for machine learning pipelines, our main library that we're using is Kedro. And Kedro provides an open source framework for building and running modular data science code. And Quantum Black, the company, came up with this, owned by McKinsey. Really, the core idea behind Kedro is that it creates directed acyclic graphs, which are comprised of functions and data sets, and which are connected together to create a pipeline that can be executed in one process. So nodes in the graph are the functions that drive the pipeline. It can be data transformations, model training, feature engineering or selection, are examples of node functions that we might be using. Kedro provides a very nice data engineering convention to track data transformations across local and cloud data stores. So we're having sort of the same data engineering done on local machines and also in the cloud. So we can easily track each type of data set we're using throughout a given pipeline. So here's a little bit of example of that data engineering convention. So we have different layers going from the raw data, no processing whatsoever, and that goes into sort of an intermediate layer with maybe some cleaning or cleansing or a bit of data wrangling done, and then sort of a primary layer that could be the fully clean data that you would want to start the machine learning process at that layer. And then a feature layer where we log different features that have been engineered or that are directly sets of features that are directly engineered at that layer. And the model input layer, which are data sets that are going directly into the models themselves, which can be saved as pickle files or other files, and the outputs of the model, predictions or other artifacts, and then a reporting layer that shows sort of everything that happened during the training runs and the cross-validation reports. So we have here on the right-hand side, we have an example of this directed acyclic graph that Kedro provides. And you can see that at the top, we start with a data set and some parameters. That goes into a function called process data. That function's executed, and the outputs of that function, let's say it splits the X and Y from the training set, and then some more parameters are hooked in. That goes into a function called train model. Test set is created for X and Y as well. So those are other arcs going across on the right-hand side. another function called train model is executed. The output of that is the model artifact. That goes into a function called predict, and predict along with the X-test data set, and the predictions are output from that. And then you can see at the end, we have predictions and Y-test going into a reporting function for the accuracy. So that's just an example of what Kedro allows you to do in one modular pipeline. So another key component of the workflow is MLflow. And MLflow is an open source platform that for managing machine learning life cycles. It allows for experiment tracking, easy reproducibility, deployment, and registering models. It allows for multiple users to connect to an MLflow instance and run their experiments in different compute environments and log all the experiments together. And these MLflow allows for easy deployment of models to web applications through REST APIs to serve predictions. Let's say if you're doing machine learning in a web application. And it allows for easy versioning of models and parameters to be tracked, so we can always reproduce those models. So here's an example of the MLflow server user interface. We have a lot of experiments being run here in the main section, the different runs and the users and different parameters that have been trained on each of those models. So it logs all of that for you automatically. You can quickly just add MLflow logging turned on basically in your code, and it'll run all of this for you and do all the logging automatically. And so we can have multiple users training their models and then logging them together here. And so we can easily track and compare the outputs of multiple users. And so another really key component to this is Databricks. So for us, we're using it for ML lifecycle integration. And it's a platform that enables seamless integration of data science code, experiment tracking from MLflow like we saw, and cloud resources that we want to tap into, as well as data, of course. With Databricks, we can allow data scientists to run their Kedro pipelines, as we previously saw, on compute clusters via Databricks Connect, which is a Spark client library that connects local development environments to Databricks clusters. So we can send Spark jobs quickly to Databricks through Databricks Connect. And so we'll talk about Spark. So PySpark is what we're using for big data processing. It's a Python library that ships data science jobs to Spark clusters running with Databricks. And it works with Databricks Connect, so we can quickly translate our pipelines into Spark jobs on a local machine and then send it to the cloud to run and do training or what have you with very little friction. And so Spark has a different sort of framework of programming data sets and constructing data sets. So Koalas is a library that implements the native pandas data frame on top of Spark, which allows for very little learning curve for a new data scientist who's familiar with pandas but isn't familiar with Spark to come in and start creating pipelines in the same way that they've learned to do that. So now I'll show you a bit about the architecture that goes into this workflow. So at the top, we have sort of our Git repositories and Docker images where we we use the same Docker image for every developer. So we sort of, they're install and clone that Docker image on their local computer, and they can also install a custom scaffold repository is what we call, and the scaffold consists of sort of proprietary ML functions, custom ML functions that we built and we use over and over. It also gives you all the dependencies with all the same versions to keep the versions consistent across all developers. And our ML project that we're working on, so this scenario, we're kind of working on a new ML project, let's say. We initialize it as a Kedro project, which Kedro allows you to do, sets up the data engineering, sets up a bunch of different files you need to run the pipelines. So once individual developers are set up in that way, we can, inside of their Docker container, they develop, and on the bottom left, you see that they'll have ML libraries in there. They'll have the ability to build Kedro pipelines. They have PySpark and Databricks Connect to send those jobs to the cloud, as well as koalas to create, to work with data frames that can be sent to Spark, just as if you were working with a pandas data frame. And so once we're ready to send those Spark jobs, they can easily just be sent to the cloud where Databricks is running through Databricks Connect. And on the right-hand side, we have in our, let's say we're working on Amazon, we have our S3 bucket where we have adopted Kedro data engineering convention in there as well. That's identical to other individual machines for this given project. And so we have in our cloud environment, we have Databricks, which is allows connections to our cloud storage like S3 or databases. We have MLflow that is easily connected to Databricks. We have our training compute and deployment compute. So once we run our jobs, we do the training and we can quickly deploy. We can do continuous training and deploy models to production applications directly through commands directly from local environments. So once the cloud is up and running in this format, we can just continue to develop locally, send these commands to the cloud, and it'll do all these training and compute functions with no friction. So I'll walk through sort of an example scenario. Like we're just starting a brand new machine learning project, requires some research to get to a workable model that we want to put into production. So we can start the project setup. We initialize a Kedro project template, step one at the top here. Okay, there's my slide, step one at the top here. And we clone the repositories and correct necessary libraries like Databricks Connect and our dependencies into and build the development training containers. And on the Git flow side, we're initializing master and development branches within the project setup. And so step two, we're compute-wise, we're on our local machines or individual cloud instances. And we are working with our data engineering, we're creating pipelines with pandas, prototyping pipelines with pandas, and other scientific machine learning libraries in Python. So we're sort of getting a sense without going and using cloud resources, what are some promising ways we can start the modeling. We can log these local experiments in MLflow in the same manner. And so for this part of the process, each data scientist has their own feature branch where they're working. So all of their individual experiments are logged in there, so they can do whatever they want experimentation wise on their own feature branch. So the next step would be to go to the cloud, and we'll be working with koalas and PySpark. And in this case, we've done enough experimentation that we want to train on lots of data and really do a full training run on all the data, not so much prototyping anymore. From the individual experiments, we found that we found a promising solution, and we can train this candidate model on all the data. And so we just do that in the cloud through Databricks Connect using koalas, and can register that model in MLflow as well. And then we'll commit that code to the development branch and add any new functions to our scaffold library as well. And then in step 4, we are going to select a final model that we want to put into production. And we'll use the same Databricks Connect with the inference compute. And on the engineering side, we're still using koalas and PySpark. And we're going to deploy that final model through MLflow and Databricks, and commit that code to master. It's sort of a production 1.0, if you will. And so in step 5, we can basically introduce continuous retraining. So with that final model, when new data is received in the production environment, we can train the model with an automation of that pipeline that was the final pipeline, and automate the retraining and logging and reporting as well whenever new data is received. So that constitutes the full workflow that we are using here at Trillion Technology Solutions. And I'm excited to take your questions on this. There should be a lot of discussion. I think a lot of you are working with a lot of these tools as well. So I'm interested to hear your feedback, how you're using some of these tools together, what systems you've designed to work with multiple data scientists on a project as well. So thank you very much.